Good day, everyone. I am Lugaz from University of New Hampshire. I'd like to talk to you about how to do advanced warning of interplanetary transients, specifically coronal mass ejections and shocks, and why do we need a research mission or more research in general before going into operational. So, as most of you know, the most important thing to forecast space weather is to measure the interplanetary field, the proton velocity, and dynamic pressure. That shocks and coronal mass ejections are the major driver affecting space weather. Measurements at the Lagrangian 1 point, or L1, currently by Discover, but soon by Swift L1, provide about a 1-hour warning of incoming CMEs and shocks with very high accuracy. A very straightforward idea to get more advanced warning is to go closer to the sun than L1, which is what a sub-L1 monitor is. Ideally, this will be complemented by remote observation, such as L4 or L5, as provided, for example, by ESA with the Lagrange mission. But also they can provide more advanced warning. They cannot provide accurate magnetic field forecast. And you can see what I'm already leading into is this idea of lead time versus accuracy of forecast. To my knowledge, this has not been extensively studied in space weather, especially for coronal mass ejection. If we focus on forecasting a CME or the effect of a CME after it occurs, so not talking about flares or SCP effect, we can forecast the CME arrival time and speed with off the Sun-Earth line remote observation, currently by stereo, with a lead time of maybe 1 to 3 days. However, the accuracy may only be about plus or minus 10 or 12 hours in the arrival time, which is something I'll qualify to moderate to low. If we want higher accuracy, potentially, forecast with lead time of maybe 2 to 8 hours, we can do so with sub-L1 monitors, so measuring the CME at 0.8 AU, for example, or 0.2 AU from Earth. And ideally, we'd want to do both. We'd want to have both remote sensing for advanced warning and the in-situ measurement for much more accurate warning. And very much, it's very similar to hurricane forecasting, when you have GOES spacecraft taking remote observation of hurricane forming off the coast of Africa, maybe 7 days or 8 days before it impact anything, and then your radar just off the coast of Florida, which is going to give you the accurate measurement of the speed, maybe 1 or 2 hours before it impacts. And really what we want the same thing in space weather forecasting. In terms of this idea of lead time versus accuracy of the forecast, there's been a recent example of this for solar wind streams, or SIRs, which is a study by Bailey et al. From the space weather from in space weather in 2020, which is a relatively complex plot, but they looked at how well does stereo B does in forecasting what's going to happen at Earth as stereo B was moving away from Earth. So this is kind of the separation between stereo B and Earth in degrees, and this is a correlation between various measurements. Focusing on the BZ in purple here, you can see that by the time you reach L5 or 60 degrees, the correlation is pretty much 0. However, there's probably a sweet spot between lead time and accuracy, which might be about 10 to 30 hours, or maybe about 10 or 30 degrees, sorry, which is about maybe somewhere around 1 to 2 days advance warning. So not as good advance warning as L5, but much more accurate things. Of course, going to L5 is a technological point where you can stay there relatively easily. So that's where technology comes in addition to knowledge. So really is a question, do we have the technology to build such sub-L1 monitors and to launch them? And the answer is yes. We can build them certainly and launch them, depending on which technology, where you want to go. Some of the technology might still be in demonstration phase, but with NASA having selected Stack Demo, which is a solar cell to be launched alongside IMAP, we'll have IRTL even for solar cell in a few years. Now the real question is, do we know where we want to go? Do we have the physical knowledge to determine what is the best orbit for a space weather mission? And again, that's a question of how far from the Earth we want to go, so the lead time of the forecast, and how far from Sun-Earth line do we want to go, which is probably the accuracy of the forecast. And in fact, there's been numerous proposed sub-L1 missions dating back to about 20 years ago. with various orbit and various technology, which are shown on this plot, where in the x-axis, I'm kind of showing the radial distance from Earth. So farther away would be more lead time. And the y-axis, I'm showing the distance on the Sun-Earth line, which potentially, but hard to quantify at this time, would be accurate as a forecast. So for example, we have L1 here at the corner, solar cells right now, probably staying relatively close to Earth, but also able to stay very close on the Sun-Earth line. Then you can have any kind of distant prograde, distant retrograde, or stereo-like orbits, which are kind of intermediate. And on the high end, unless you have hundreds of spacecraft, would be, for example, going to Venus and launching maybe 12 spacecraft, which one of them will only be 0.3 AU upstream of Earth and 15 or so degrees away from the Sun-Earth line. So we need to understand which one of these concepts is the one we want to go forward. Let's take a few seconds and ask yourself this question. What is more valuable? Is it measuring a CME 10 degrees from Sun-Earth line at 0.8 AU? Or is it measuring a CME at 1 degree from Sun-Earth line at 0.95 AU? If you know the answer, come to the live session. Let's chat about it, because I personally really don't know. And the reason I don't know is because we haven't had enough measurement of CME at this kind of separation and this kind of distance. And the few CME we have had have revealed that you can have significant difference in terms of shocks. That's a study by Coronal and Szabo in 2010, and sheath and ejecta, which is studied by myself and Halalati this year, in, again, less than 1 degree separation. That's using wind, distant prograde orbit in 2000-2002, as compared to ACE measurement. And what we find, which is summarized in this plot by Halalati, is kind of these bars represent the correlation lengths of measurement inside the CME sheath and inside the CME ejecta. And you can find that correlation lengths are kind of on the order of 0.1 to 0.2 AU. So if you go much farther than that, you should expect, even in CME, even in a large scale object like the CME, no correlation. So if you go beyond 10 degrees, you should see no correlation between what you observe in this L1 monitor and Earth, and that's very problematic. I say, okay, that's just a statistical study, I don't really believe it. Well, if you don't really believe me, or if you don't wonder about this question, think about this event, which is pretty much the only nice event we had with stereo after its launch in 2007, when it was still close to Earth. And stereo A, which is shown here on the right-hand side on the middle panel, and wind were separated by 6 degrees, where stereo A was about 0.04 AU upstream of Earth. So here's a situation where stereo A was an upstream monitor for L1. And what happened? Well, stereo A observed nothing, and stereo B and wind observed a beautiful flux slope. So again, it tells us that that's 6 degree separation between two spacecraft. One of them can observe something, and one of them can observe nothing, even inside a large-scale structure like a CME. A very recent example is the first CME observed by Solar Orbiter, which is currently, you can read the article in Archive by Emma Davis in the AI topical issue. L1 and Solar Orbiter were separated by about 4.9 degrees in longitude and about 0.2 AU with Solar Orbiter being upstream of Earth. You can see here in this plot. And while the magnetic field measurements were quite consistent, one thing which is somewhat surprising is that the duration of the flux slope at orbiter and wind are about the same. So if you took this, again, as an upstream monitor and say, well, how long is this flux slope going to last at 1 AU? Well, I know it should expand. You actually would be wrong by about 20%. Obviously, that's still much better than we can get from remote sensing. It's probably actionable, but we have this kind of, I haven't really studied how much errors we would have with this kind of measurements. And in fact, the core question really that we don't know much about is CME expansion. However, thanks to planetary mission, specifically Messenger at Mercury, Venus Express at Venus, and of course stereo and ACE and wind around 1 AU, we have actually enough measurements in solar cycle 24 in conjunction between 20 and 45, depending on how strict you want a conjunction to be, to actually see the difference between statistical studies and how does the CME expand between 2 points. And pretty much you can see here in this three plot between Tarek Salman, my PhD student, Bojan Viznak, and Simon Good, where here showing the magnetic field decreases with distance, is showing the size increase with distance, where this solid line, dash dot line in Bojan plot are statistical study, what you expect on average. And any 2 points actually are a set of events measured to spacecraft. And you can see there's a lot of variability. Statistical study tell you what is the average, but any actual CME might deviate significantly from the average. And what drives this change, what drives this variability, you actually don't know. That's a follow-up study I did recently in APJ in Lugaz et al. 2020, where we looked, for example, here at what is the expansion speed of a CME at 1 AU versus how much did the CME magnetic field decrease between two spacecraft. And you expect this to be somewhat correlated because the expansion speed at 1 AU is a measure of the expansion, whereas how much the CME magnetic field decreases between 2 points is also a measure of the expansion. And what we found that it's very weakly or not at all correlated. And that's somewhat surprising, somewhat problematic, and tells us that we don't know what drives this variability. We looked also at the CME speed, at the CME size, and really could find no correlation between how does the CME magnetic field change between 2 points and any of the CME properties. So if this is true, and it should be completed with better studies, with more measurement of the plasma, for example, it would be problematic for Sub L1 monitors because we wouldn't be able to use statistical studies because there's a lot of variability. Also, we won't be able to use some of the information we have from in-situ. And it's really because we don't know how well things evolve on relatively moderate timescales and scales. So to go back to our main questions, that these Sub L1 monitors, well, we know how to build them, we know how to launch them, we know how to operate them, but we don't know where to put them. And it's really a question of the operation side of where to go, how close to Earth and how close to the Sun-Earth line, and goes back to actually physical knowledge question, which is how do CME properties vary on scales of maybe 0.1 to 0.3 AU, on longitudinal scales of maybe 1 to 10 degrees, and going back really a step further, what is the structure of CME, what is the structure of shocks in 3D? And if we don't know that, then it's very hard to use warning from a spacecraft that will not be exactly aligned to forecast what's going to happen at Earth. And so ideally, before launching an operational mission, we want to answer these questions. Ideally, we want to answer both the operational and the science question. And to do so, what we're pushing for with colleagues of mine from UNH and Berkeley is a small platform, pretty much using the same instrumentation as with L1, so a magnetometer on a boom, proton and alpha measurements, and electron measurements, and energetic ions and protons and electrons, maybe with protons up to 10 or 20 MeVs. And the main idea is you want to be high TRL, don't push for fancy instrumentation, no time of flight, no remote sensing, because remote sensing is add a lot of mass, a lot of telemetry constraints, keep this thing as light as possible. Themis has shown that pretty much 20 years ago, almost now, 15 years ago, you could do this on a 70 kilo dry bus including payload, add 50 kilo of hydrogen and get enough delta V for Themis to go from its orbit around Earth to go to a near cislunar orbit. So more than a kilometer per second of delta V. And with such a mission, we could actually answer both the science question and the operational question. So again, no remote sensing, as I said, also allows you to either slew or rotate. And really want to launch this as a rideshare. Rideshare with mission to the moon, to cislunar, to interplanetary space, planetary mission. So I have some of delta V, not extreme, maybe about a kilometer per second or so. And so it's totally possible to do so with a total mass of maybe 120 kilo. So with this, you should be able to launch on as many rideshare as possible. And then where you want to go, it's really up to you. Not pushing specifically for orbits. It could be a stereo-like orbit, a distant retrograde orbit, Earth return orbit, or so on and so forth. The main reason you cannot really go into CubeSat mode is because you still need this space network and with a pretty big radio and antenna to be able to do telemetry, and potentially to do a beacon mode where you could actually test for part of the orbit how well does it do in real-time forecasting. The last thing is cost, and we estimate this to be about $60 million for one spacecraft and 20 million extra for any additional spacecraft, so that for SMEC's budget, you could do a 3 or 4 constellation and go after both space science and space weather goals. Thank you.